Hello chemists, this is Ms. Placino and you are watching Screencast 1.5 on the history of the atom. In this lesson we're going to talk about how the theory of the atom has evolved over time. Our modern day view of the atom is the work of many scientists over many years, and we're just going to really get to the tip of the iceberg today and talk about some of the first experiments and models that were proposed. So if you missed class today, you missed out on kind of like a fun little activity. You were given what I call a mystery box, and basically all it was a small plastic box, and in the inside you had a ball, and then I told you that there were some barricades or some blockages set up inside of the mystery box. So I've got the ball represented by a circle, and I've just kind of drawn that other structure to be the barricade. And what your job was is to go through and figure out how the barricades were set up without opening the box. So during class, people were shaking the box, they were moving the box really carefully and slowly, they were trying to hold it close to their ears so they could hear what was going on. In other words, you were making a lot of indirect observations. Once you had had a chance to make these indirect observations, you were asked to sketch out what you thought the inside of the box looked like. And then, aside from opening the box, I asked you what you would be able to do to be a little bit more confident in your sketch, and people came up with some really good ideas. Some of them were as simple as just talking to some of your other classmates, see if they're getting the same thing. Some of you suggested trying to build a model or trying to take x-rays of the box to really improve how confident you are that you've got the right idea. Finally, I asked you to kind of draw a parallel to what we're going to study today. What does trying to determine what the inside of the mystery box looks like and determining the structure of the atom have in common? And ultimately, we concluded that the structure of the atom, just like the inside of the mystery box, had to be discovered, for lack of a better word, through indirect observations. At no point in time could scientists just kind of peek inside the atom and see what was actually going on. They had to use indirect observations, build models, do experiments, and try to piece the information together the best that they could. At the end of the activity, a number of students asked me if they could open up the box, and much to your dismay, I told you, no, you cannot open the box. And I know for some of you that's really frustrating, not getting to know, was I right or was I wrong? And there are a number of things in science that you can study, I guess in just life in general, where there is really no way for you to know if you're right or not. Just like in this activity, when people repeat your experiments and draw the same conclusions, you can be more confident in it, but there are some things you'll never know 100%. So today we're going to look at kind of the beginning of the atom and really what got scientists thinking about what the atom might look like. All right, so the first scientist that we've got here is John Dalton. If you look at page 14 in your workbook, you've got the picture of the scientist. Above him, go ahead and write his name. Like athletes, it's really the last name of scientist that's most important. Then below it, we've got space for the name of the model and a quick sketch of what the model is. And then further below that, you've got more detailed notes on the scientist. So John Dalton proposed what we know as the billiard ball model of the atom. If you've ever played pool before, you know what a billiard ball is. It's just a hard, solid, round sphere. So the structure or a sketch of what his atom would look like is just simply a circle. Dalton theorized that elements are composed of atoms and that all atoms of an element are identical. We know this to be true today. He also thought that atoms of different elements have different weights. If you check a periodic table, you'll see that he was right about that as well. And he thought that compounds are formed by joining multiple elements, and that's exactly what we do. We react multiple elements together. They're either going to exchange or share electrons to form our compounds. So this is a really good first model of the atom. There's not a whole lot of information about the structure, but again, you got to remember this is the early 1800s. They have very limited technology, especially compared to what we have today. Fast forward about 100 years and you get to J.J. Thomson. J.J. Thomson is a British physicist who is working with cathode ray tubes. And all a cathode ray tube is an electrical current that is passed through a vacuum. There's actually a picture of it on page 14. We'll talk about it in a little bit more detail on the next slide. In addition to working with cathode ray tubes, he was putting magnetic and electric fields near them and seeing how the cathode ray tube responded. or I guess I should say the ray inside the tube, how it responded. And through his experimentation, J.J. Thomson discovered what we now know today are as electrons, the negatively charged part of the atom. So just a little bit more about our cathode ray tube. We did this in class. The tube itself is made of glass, and it's nearly a vacuum. It's had most, if not all, of the air sucked out of it. Your cathode and your anode, you can just think about those as being metal plates. You've got like this white piece of paper. This isn't the greatest picture behind it. And then it looks like there's this green line, this green light that's being produced. It's really this stream of particles that's producing what appears to be this light. The particles hit that paper behind it, and it causes it to fluoresce. Otherwise, those particles would be invisible and we wouldn't see it. This cord that's attached to the alligator clip, it goes to a power source that's going to take some electricity. And then we put magnets near it, and we see how that cathode ray, I'm going to call it, that stream of particles is going to respond. And I've got a short video to show you what you would observe.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes this specially coated surface, the cathode ray produces a strong fluorescence, or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction.
Alright, so now we know that the the billiard ball model of the atom isn't really accurate, so the model has to evolve to take into consideration this new discovery. In other words, the discovery of electrons. So J.J. Thomson proposed what he calls the plum pudding model. Plum pudding is a British dessert. Chances are you're not real familiar with it, but I bet you are familiar with a chocolate chip cookie. And the plum pudding model of the atom, it looks something like this, and it does, at least to me anyway, kind of look like a chocolate chip cookie. And according to this model, the dough of the cookie is positively charged, and then these electrons that Thomson discovered, he has them just kind of randomly scattered throughout the cookie dough, much in the way that chocolate chips are randomly scattered in a cookie. So in this model, the atom itself is positive, and the negatively charged electrons are just scattered throughout. This model of the atom didn't last for too long. Just over a decade later, this physicist, Ernest Rutherford, performed an extremely famous experiment called the gold foil experiment. In your notes, go ahead and put a star over Ernest Rutherford. He is really credited with completely revolutionizing the model of the atom. In the gold foil experiment, he took gold foil and he bombarded it with alpha particles. Just to give you a little bit more information, think about gold foil being more or less similar to aluminum foil, except much more expensive. And you can actually get it thinner because you're able to press gold more than you can press aluminum. It's more malleable. All alpha particles are positively charged particles. We'll talk about them more when we discuss nuclear chemistry. So Ernest Rutherford is sitting there with a piece of gold foil and is continually throwing hundreds of thousands of alpha particles at it. And what he observed is that a very, very small percentage, less than 0.1%, of these alpha particles were deflected. The overwhelming majority of them passed right through the gold foil as though it wasn't even there. This was unexpected. Ernest Rutherford, based on Thomson's model of the atom, the plum pudding model, expected all the particles to pass through undisturbed. Instead, he saw that some of them were kind of scattered at wild angles. This may not seem like a really big deal, but to draw an analogy, imagine that you have a piece of tissue paper and you're firing bullets at it from a gun, and one of the bullets actually bounces off the tissue paper and hits you in the head. Your last thought is probably going to be, oh my gosh, that was crazy, how did that happen? And that's the same magnitude that the scientific community viewed this experiment. We have the plum pudding model. This was supposed to, I guess in a sense, kind of prove that it was correct. And instead, we discovered that, wait a second, this is not an accurate model of the atom either. There's something else going on. So I've got a quick video to show you about the gold foil experiment.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Alright, so a little bit more about the gold foil experiment. Essentially, Ernest Rutherford discovered the nucleus. This is a monumental change to the model of the atom that J.J. Thomson proposed, where that positive charge was just kind of smeared out across the entire atom. Because so few of the alpha particles actually struck the nucleus, Rutherford concluded that most of the atom is empty space. To draw a parallel, imagine that you're at a professional football stadium. You're at a Giant Stadium. It is a gigantic, gigantic stadium. And you take a marble and you place it on the 50-yard line. The stadium itself represents the atom. The marble represents the nucleus. So the atom is overwhelmingly wide open empty space, which is kind of crazy when you think about it, that like the chair that you're sitting in is mostly empty space. The other thing that Rutherford was able to conclude is that at the center of the atom there must be a very small, very dense, positively charged entity. In other words, the nucleus. He knows that it's small because the alpha particles hit it so infrequently, and he knows that it's positively charged because the alpha particles are deflected from it. He probably can conclude that it's dense because that's where all the mass of the atom is. The electrons are essentially massless. So our model of the atom has changed. It's starting to look a little bit more like the model of the atom that you're probably familiar with. We call this the nuclear model, and in this picture we've got the red nucleus. We know that it's positively charged. We still don't know about protons and neutrons just yet. That discovery comes years later. And those little green dots are supposed to represent the electrons. So we've started to shape up with a more realistic model of the atom. Finally, the last scientist that I want to talk about today is Niels Bohr. And in 1913, Niels Bohr proposed the planetary model of the atom. Essentially, in Bohr's model of the atom, you've got the nucleus at the center of the atom. That's this big red dot in the middle. And then you've got these orbits, he calls them, that the electrons revolve or orbit around the nucleus in. So if you kind of draw a parallel to the solar system, you've got the sun at the center of our solar system. You've got planets orbiting around it in very well-defined paths. We're going to spend more time talking about Niels Bohr next unit as we really delve into electron configuration. It turns out that Niels Bohr's model, it really only works for one element in the entire periodic table. The model that we have today is much more complicated than the planetary model, but I don't want to ruin any surprises for you just yet. All right, that wraps up our quick history of the atom. Make sure you're taking the time to really familiarize yourselves with the different models and understand the discoveries or the changes that led to that previous model of the atom needing to be updated.